Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 8. Solving two-point nonlinear boundary value problems using finite difference method. Two-point nonlinear boundary value problems are a common and important class of problems in applied sciences and engineering. These problems involve ordinary differential equations that are subject to boundary conditions at two distinct points, usually at the left and right endpoints of an interval. The key characteristic of these problems is the presence of nonlinearity. When the differential equations are nonlinear, solving them analytically is often challenging. Hence, numerical methods are generally employed to find approximate solutions. Consider the following two-point nonlinear boundary value problem subject to Dirichlet boundary conditions, where A and B are known real constants. Furthermore, assume that f is continuous on the domain x, y prime are real in the solution interval, partial derivative with respect to y, and partial derivative with respect to y prime exist and are continuous functions on D. Partial derivative of f with respect to y is positive, and partial derivative of f with respect to y prime is bounded on D. The preceding assumptions guarantee that the boundary value problem defined by nonlinear ordinary differential equation has a unique solution. The numerical procedure presented in this lecture can be similarly and easily extended to nonlinear two-point boundary value problems with mixed boundary conditions. Now let's go over the steps of numerical solution. Step 1. Gridding. The computational domain is divided into uniformly or non-uniformly spaced M subintervals, and grid points, or nodes, are placed at the endpoints of every subinterval. The nodes are enumerated, starting from either 0 or 1, and abscisses of the nodes are calculated from xi equals x sub I minus 1 plus h sub I minus 1, I equals 1 through m, where hi may be constant. The objective is to find the ordinates, yi's, which are the unknowns. Step 2. Discretizing. In this step, the solution function as well as its boundary conditions satisfying the boundary value problem is transformed to a discrete function. A two-point nonlinear ordinary differential equation is satisfied for every x in the solution domain. So the differential equation is discretized at a node xi. The first and second derivatives appearing in the differential equation are replaced by the central difference approximations. Then the ordinary differential equation for the ith nodal point, x equals xi, is expressed as follows. Step 3. Implementing the boundary conditions. A Dirichlet boundary condition is commonly encountered as a fixed temperature, pressure, velocity, and so on at a boundary. This means that the physical quantity at the boundary node is known. This condition is generally incorporated into the solution process as a difference equation as follows. In other words, we treat the node as unknown but set the coefficient of central node to 1, the right-hand side of the equation to the fixed boundary condition value, and the coefficients of the neighboring grid points to 0. Newman and Robin boundary conditions can be implemented as in linear boundary value problems. Step 4. Constructing a nonlinear system. The discretized equations with the boundary nodes yields the following simultaneous system of nonlinear equations, where y and g are the vectors of unknowns and right-hand sides corresponding to the nodal points. Also note that the nonlinearity is introduced by the function f. Step 5. Solving the linear system. The nonlinear system of equations is solved iteratively using a method such as fixed-point iteration, Newton's method, etc. Here, we will describe the implementation of Newton's method. Initial guess is crucial for the convergence of a system of nonlinear equations with iterative methods. A two-point nonlinear boundary value problem subjected to Dirichlet boundary conditions, ya equals uppercase A and yb equals uppercase B, is unique in that a smart initial guess can be roughly prepared using linear interpolation as follows. The advantages of the method are: finite difference methods are ideal for treating unstable nonlinear problems. The resulting tridiagonal system of equations can be efficiently solved using Thomas algorithm. If a boundary value problem converges, it converges quadratically. The disadvantages of the method are: finite difference method may lead to a large number of simultaneous nonlinear equations, requiring iterative schemes to achieve an approximate solution with the desired accuracy. A smart initial guess or a rough prediction may be necessary to ensure convergence. Newton's method, which is one of the most commonly used methods, can be effectively applied to solve nonlinear equation systems. See section 4.8. The method leads to an improved solution of the following form, where the delta vector is the displacement vector at the pth iteration step, obtained from solving the following linear system of equations, where J, Y, is the Jacobian matrix defined as a tridiagonal matrix as illustrated. The components of the tridiagonal matrix are: for a simple function f, the Jacobian can be easily constructed analytically. For functions containing more complex expressions, numerical differentiation is necessary, which also contributes to the approximation errors. Consider the following second-order two-point nonlinear boundary value problem. Use the finite differences together with Newton's method to obtain approximate solutions to the given problem for the uniform step sizes of h equals 0.2, 0.1, and 0.05. Then, compare your estimates with the given true solution. Now let's go through the solution procedure step by step. In step 1, the gridding step, we create discrete nodal points for which the solution are sought. Here, we will illustrate the details of the numerical solution for m equals 5. We divide the solution interval from 0 to 1 is into 5 uniform subintervals giving h equals 0.2 and place nodes at the endpoints of every subinterval. The nodes are enumerated, starting from 0, and the abscissas corresponding to the nodes are calculated from xi equals 0.2 times I, for I equals 0 to 5. The grids are illustrated representatively in this figure. The left and right boundary conditions are Dirichlet type. However, we will treat them as unknowns when setting up the system of linear equations. In this regard, we have 6 unknowns, including boundary nodes. We need to find 4 more equations. In step 2, the second derivative is isolated. The given differential equation is satisfied for every x from 0 to 1. The highlighted function f is also found in this step. The ordinary differential equation is discretized at an arbitrary node xi by replacing the first and second derivatives with their central difference approximations to give the following general difference equation. The boundary conditions for this particular problem are Dirichlet-type boundary conditions. We will embed the boundary nodes as unknowns with appropriately defined, discretized difference equations in the general nonlinear system. The left boundary condition, y0 is equal to 0, is expressed as y sub 0 is equal to 0. The right boundary condition, y1 is equal to 2, is expressed as y sub 5 minus 2 is equal to 0. A unique 6 by 6 system of linear equations for the displacement can be expressed in matrix form as follows, where the superscript p denotes the iteration step. The current step solution is then obtained from the components of the tridiagonal matrix are obtained as follows, where we also find partial derivatives of f with respect to y and y prime. The resulting 6 by 6 system of linear equations are solved iteratively. Since the boundary conditions are Dirichlet boundary conditions, the initial guesses for the nodes between the boundary points are obtained by linear interpolation. The iteration procedure is continued until the norm of the displacement vector is less than a tolerance value. Note that the tridiagonal matrix elements will be updated at every iteration step. For the first iteration, we obtain the system of linear equations as follows. Notice that the right-hand sides of the first and last rows are set to 0 because we do not want the initial conditions assigned by the initial guess to change. At the end of each iteration, the norm of the displacement vector is calculated for the convergence test. In this example problem, Newton's method converges with an error of the order of 10 to the minus 11 after 4 iterations. The true absolute errors of the solutions obtained for uniformly spaced 5, 10, and 20 intervals, as well as the true solution, are presented in tabular form. For m equals 5, the magnitude of error is about 10 to the minus 2, and when the number of intervals is doubled, the magnitude of the error decreases by about 4 folds. When the true solution is examined, it is observed that there is a considerable change in the curvature of the true solution in the interval from 0.05 to 0.2. That is why the errors in this range are a bit higher. With this note, we conclude this video lecture. That is all for now. See you next time with another topic. Bye.